Machine/computer vision. The last day one topic panel explored the progress and future potentials of computer vision and what we can anticipate in the coming decades. Speaker bios are at futureofinterface.org/bios.
I have with me four remarkable panelists, Aude Oliva, who's from MIT, Dacheng from the University of Sydney, Marshall Hebert, I hope I said that right, Marshall, from Carnegie Mellon, and Tom Duerig from Google. The question is, where are we going to be 20 years from now in computer vision? And I'd like to preface this by making a couple of naive layman's observations, which means my paper-thin knowledge of machine vision. One thing is that it's one thing to try to interpret a scene and figure out what's in it, and maybe even what's going on. And you can imagine a certain amount of machine learning training with images to explain what it is that you should infer from it. But the thing I wanted to ask you about has to do with the ability of an algorithm, let me use that word, to look at a scene and recognize how to decompose the scene. So as an example, if there is a cup on a table and it's part of the scene, will we get to the point where it will be understood by the computer that it's separable from the rest of the universe? And it's always been my thought that unless our vision interpretation systems have the ability to experiment with the real world, to move things around, to discover things are not connected and not part of the other thing, or by moving around in order to see around objects, that the real world becomes more understandable. Humans do this because we interact with the real world. We discover things by picking them up and moving them around, or walking all the way around. So where are we likely, let's say 20 years from now, to anticipate a capability more like our own, which is to recognize the real world in the images that we're looking at? And so I'm going to offer an opportunity for each of the panelists to respond, not necessarily only to that question, but more generally framing view of where we're going in computer vision. Let me start with Aude and ask you how you would respond to that.
Yeah, thank you very much. This is, I think, a very important question, one of literally the keystone question of how the field of computer vision could move forward. And on the one hand, for most of us working in computer vision, we think about a 2D screen, or we can even think about a sort of virtual reality where we will have a 3D. And there's a lot of, most of the methods out there right now do not take into account the other camp, which is the fact that you will have an agent that experience the world like we do. It could be like a robot, or it could be an agent that is moving through the world. And I wanted to make a link with the human brain. I'm fascinated by neuroscience. I'm also a neuroscientist. And there is something that maybe not all of us know, is that actually in the brain, there is different region dedicated to the object that we will pick up with our hand, small object, versus larger object of space that we will navigate through with our body. So a chair and a sofa will be located more in a different part of the brain than the small object we are picking up. And this is certainly an ability we are learning as people evolving into the world when we interact with the world. So how to have this physics of the world embedded into the knowledge of the future computer vision system is really a very challenging question, but something that we could see will progress in a few years, the next few years.
Wow. Well, thank you for that. I think that the question that I'm posing is not unlike the question that arises in the case of text material, where we wonder whether the meaning of the text is understood by the machine learning system or whether it's just grammatical construction. But that's not today's topic. So let me move on to Dacheng and ask if you would like to respond to this question.
Thank you, Vint, for your kind invitation and this wonderful question. And I think Audi offered a very nice perspective regarding the next 20 years for where we can see our machine vision will be. So regarding machine and computer vision, so I personally think we may consider four major tasks. So that include the object recognition and the localization, the 3D reconstruction, multimodal learning, and also the learning in the virtual reality environments. So within around 20 years, I think our machines will be capable to accurately recognize and localize objects, even for very tiny and fast-moving objects. We know we still have we have a lot of challenges here, and that will be able to efficiently identify hundreds of thousands of, or even millions of object categories with a very high accuracy, and to segment these objects into finer parts regarding semantics or functionality. Therefore, it is a time machines can fully understand the real-world environment, and the machines can duly operate with those objects. Now, the 3D reconstruction is still a big challenge. I expect the next 20 years, with the faster development of sensors and deep learning, machines can efficiently and accurately reconstruct real-world things using color and depth cameras, even the cameras, LiDAR, and maybe some new sensors. The development of 3D reconstruction technology will enable the creation of virtual environments that closely resemble real-world things, providing new opportunities for exploration and analysis. In addition, such kind of 3D reconstruction technologies will play a critical role in areas such as virtual and augmented reality, where realistic and immersive environments are essential. In these days, I believe most researchers have paid more or less attention to ChatGPT. And I also believe by leveraging multimodality data, such as text and image, speech and image, or the integration of text, video, speech, image, audio, a lot of things, so that we can conduct cross-modal learning, where we can enormously enhance the visual perception and generation, even in few shots or zero-shot settings. This will enable machine vision to better understand and the use of the context and the relationships between different forms of data, leading to a more holistic and nuanced understanding of the world. In addition, multimodal learning will provide new opportunities for machine vision to interact with users in a more natural and intuitive ways. We know that 2021 is the first year of metaverse, at least from the industry. We have this recognition. We have observed that metaverse will transform the industry by largely improve its productivity, evidenced by the successful collaboration between NVIDIA and BMW. This suggests many activities will be moved into the virtual world, especially learning in virtual world will also enable machine vision models to be trained on more diverse and varied data, leading to more robust and generalized models. Thus, we can foresee virtual reality environments will provide new opportunities for researchers to study and test machine models in a controllable and scalable way. So we can find that there are a lot of autonomous vehicle test bed built in a virtual environment situation. Okay, so this is just my perspectives. Thank you.
Thank you very much. I would make one observation that I think are implied by what you were talking about. And that has to do with our ability to generate and simulate the real world and present the sensory input to, for example, a self-driving car. At Google or at Alphabet, we have a company called Waymo, and it's my understanding that in order to test its ability to interpret real-world signals, we generate signals that emulate what one might see in what might be sensed in the real world. And we can experiment with situations that we wouldn't want the car to actually be tested on until we're sure it will work, like the little kid that runs out between the cars with the ball, and we don't want to actually, run over the kid to find out whether our car is detected correctly. But we can send the sensory information into the system to simulate that and allow us to experiment with billions of different possible combinations. Well, sorry, I didn't mean to go too far down that path. We're going to come back to that question. Marshall, maybe you could respond now to this same question about how far can we go in terms of understanding the real world with the sensory systems of the future.
Yeah, thank you, Vint. Let me comment on two things that were said just before and then offer an additional point. First, Aude mentioned this idea of shared knowledge about the physics and geometry of the world. The idea of being able to acquire that shared knowledge, but not just learn that shared knowledge, but how to share it across different vision tasks, I think is central. Regarding Dacheng's mention of language, there's ChatGPT, of course, but there's some intriguing development in zero-shot object detectors using CLIP and that kind of thing. It's very intriguing. It's moving very fast. And to your question, I think 20 years from now, the students will wonder, why is it that we ever thought we could do things with language and vision, completely in separate threads, right, of research and thinking. So I think we're going to see big things happening there. I don't know exactly what they are, but in merging the two views. The last thing that I wanted to add is reacting then to, you use words like interaction and exploration. This goes to the broader point of moving from a world where we learn vision things from highly supervised and labeled data to a world where we learn things from a completely unsupervised or whatever word you want to use, but without human help. Another word that is important there is curiosity. There is an idea of curiosity-based learning, which is basically along the lines of exploration. And there's a lot of work there and a lot of potential, basically, to end up 20 years from now, perhaps, with systems that do not rely at all on this tedious manual labeling. Not only it's tedious, but it introduces biases that basically, limit the performance of the system by introducing our own biases.
Well, I want to go to Tom now and then come back to you with another question. But Tom, how are you looking at this 20-year period?
I'm excited about it. And I agree with almost everything that Marshall and Aude said. And I think 3D is also going to be really critical. Dacheng's point about the ability to reconstruct, informing our ability to understand. I think that's a type of supervision that may not require embodiment, potentially. I think we will be able to get to meaningfully solved computer vision without full embodiment. It's a bit controversial, but I think what we've seen in language is that this kind of masking with huge data can teach you a ton. We should be able to learn this is how coffee cups move without needing to actually poke at them. It's a bit like social psychology or these places where you don't want to run experiments versus a place where you can run your controlled experiments. Yes. I think there's enough data in the world that we don't need necessarily the ability to poke at a coffee cup to learn about it. But I'm hugely enthusiastic about not just 3D reconstruction, but generative algorithms and creation in general, powering our ability to understand the world. If we can, with high fidelity, change your coffee cup into a bottle of water, that requires a level of understanding. And that's where we are. And that's one of these remarkable transformations in the last year that I think in 20 years, we'll look back and say, all this supervised data was a little silly. You can learn it from pictures. you can learn it by reducing the information content, finding the minimal set of tokens that can generate these things, and then lay language on as an after layer. And I think that's the big dream. If I got to pick a big goal for 20 years, it would be a vision first model with semantics and language attached afterwards, such that the biases in language and semantics are secondary and don't influence your perception of the world, but instead are grounded in the real world and then, expressed via these potentially biased representations. And thank you so much. This is a remarkable group. I appreciate the fun question.
It's a fascinating question. So I'm going to pretend to channel Judah Pearl, my good friend from UCLA, who is well known for a couple of his books on machine learning, and in particular, Causality is one of the books that I would draw to your attention. He points out that the things that we discover with correlations that are driven by the kind of Bayesian models that we are exercising in a variety of ways today, those correlations, of course, don't tell us anything about how the world actually works. And so the thing that I'm struggling with as I think about your work, all of your work, is the ability of our systems to discern and to create a model of what it is that they are seeing in such a way that they can reason about the model. I mean, this is a little bit like watching birds solve problems. Very common problem that we invent, artificial problem, is to put a peanut inside of a bottle that has a hole in it, but the bird's beak can't reach the peanut. But if the bird gets a twig, it can figure out how to push the peanut through the hole and then get the peanut and eat it. And many birds figure this out. And it is my naive belief that they must have formulated a kind of model, some sort of a model that they can reason about. The models that I understand we have today with the sorts of very large language models or other large state models is statistical in nature. But I don't find that very satisfying when it comes to problem solving. It doesn't feel like that's a good match. How are we doing in representing models about which one can reason, derived from visual imagery? I don't know if that's a well-formed question, but
well, maybe I can start with one attempt at an answer from, but it's not exactly the context that you're using, but let me use a slightly different context that has to do with understanding dynamic scene, and understanding dynamic scene not just in the sense of classifying what is happening now, but forecasting what might be happening in the future.
Okay.
So there's a lot of progress in that field. And by the way, in the sense of interfacing, different agents interfacing with each other, be it self-driving car, people, whatever, it's extremely important topic. And there's a lot of progress in there. And this is an area where there's kind of an intermediate representation, if you will, that is not purely statistical, right? But is also not a purely symbolic kind of reasoning type of thing. So there's a lot of progress in that. It's a very difficult area, but I think that's one where we're going to see a lot of future development. But that's one example where there is a level of reasoning that looks at future trajectory, future motion, future decisions, for example.
So I'm going to, others may want to respond to this question, but I'm going to jump in with something. You said something super important to me, and that was forecasting and predicting. My impression of the way the human brain works, and maybe other brains work, is that they're often predicting what is going to happen and then testing to see whether or not the prediction is matched, and then adjusting if the prediction is wrong. And certainly, if you look at the large language models, they are all about prediction because they're predicting what is the next best word to stick on the end of the growing sentence or paragraph that's being added. What is the most likely thing to add to it? So prediction may turn out to be extremely fundamental to the way in which brains work and the way in which we can learn to reason about what we know about the real world. So are there others of you that might want to opine on this question of model building and reasoning?
Well, taking the human brain approach, so I think we have a tendency to separate vision, language, touch in computer vision as well as in neuroscience. But for the brain, it's a mesh of everything. So we see, but what we represent is a multimodal. So I think the field is going to see more and more system that will have multimodal access to multimodal information, and those systems are not biological. So they could have access, and they do already, to radar sensor, heat sensor, Wi-Fi can give you information about the localization of the object, or which object move, and so on. And that's a collection of sensors we have no qualia for. Well, heat we do. Okay, we can sense that. But you can now imagine a system that even if the input or the output is based on vision, because we are watching something on TV, or something is being deployed in real time on a computer, the embedded space, the representation of the system might be very this multimodal sort of meatloaf, really mesh. And you might be surprised at what the kind of reasoning the system could do that can still be based on correlation, but at some point, correlation between a new set of sensors may, in many cases, approach causality. So I'm all for finding new model approach that will really look at the causality aspect. But let's not forget that other paradigms may emerge because of additional sensors.
Let me just test you, not just Aude, but all of you, on the following scenario. Everybody knows what a table is. A table is a flat surface perpendicular to the gravitational field. Of course, no one thinks of it in those terms, but that's primarily that's exactly what it is. It holds things up against gravity. It is astonishing how quickly a 2-year-old will figure this out. And from a small number of examples, which is again something I want to probe with you, is how we can get our artificial systems to learn from small numbers of examples and then to speculate and generalize. So the 2-year-old figures out that the table is this flat thing, and then it realizes that as long as the objects that it puts on the table have a flat bottom, then they'll stay there as opposed to rolling off the table. And then they discover that a chair could be a table because a part of it is a flat surface perpendicular to the gravitational field. Your lap could be a table, a box could be a table. And what I find astonishing is how quickly the 2-year-olds are able to create models somehow and then reason about them and then extrapolate and generalize. So I guess the question I have for you is, if we're looking now 20 years out, do you think that we will have systems that are capable of observing a scene, even if not interacting with it, and being able to generalize from small numbers of examples to understand the possibilities that scene implies, or the affordances that what it is seeing will permit? Remember, you've got 20 years to get there.
Yeah, very good question, Vint. So I personally think so it is very possible, so we will be there. So roughly, so given the success of the current foundation models, especially in computer vision, we have some observation. The first is once we have a foundation model trained on a broad data, So we find that we can adapt such kind of foundation models to a specific task without using intensive training. So that means in the future, it's very likely that we have a supermodel, and such model already observed enormous amount of images, videos, or read a lot of textbooks. And so such kind of model can appropriately link information from the image domain, the text domain, and also maybe the audio domain. So that in the near future, once such kind of a model can be adapted to a specific task, so it is easily to understand what the object is and how to appropriately segment the object into finer parts with a specific functionality. And so that the vision model can understand the object and can find ways to cooperate with this object. So this is the empirical observation. And another thing is that by using the generalization analysis, we find that the trend is actually the foundation model plus fine-tuning on a narrowed down task. So it's mainly because it is a pre-training stage, but we really need a lot of data so that we can appropriately fit our large scale model to the data. If we don't have enough data, so that means our large scale model will be easily overfitted to the small scale data. And once we go to the narrow down task, we don't have a lot of data. We find that if the model is well trained, so that means it offers a very good starting point, so that we can still use stochastic gradient descent to reach somewhere very quickly. So that means we don't need to have a lot of downstream task data to complete the fine tuning. So this is my understanding. Okay, thank you.
Thank you very much. Others who want to respond to that?
I'd be happy to say a word, yeah. I suspect in 20 years, we won't have to fine tune, and it will take less effort to convey your definition of a table to one of our vision models than it would to a 2-year-old. This is my guess. In that if the definition is, please don't put a cup on it without a coaster, it's a real table, you can get that with a couple examples. Or if the definition is it might hold your thing without it rolling on the floor, again, that can be conveyed either in natural language or with very few examples. I'm hoping this paradigm of taking foundation models and fine tuning them per task and letting them fork off will simply go away as the few shot, zero shot capabilities of our models increase. And it'll be more and more just conveying to the vision systems how a human would our definitions. And I think specific task-oriented supervision, so you can reason about the world explicitly, interact with robot appendages or people in a meaningful way. This will be relatively easy to add on after you have sufficient supervision at large scale.
So the thing with, go ahead.
Yeah, I wanted to add something about people, human brain, and exactly your question is, to me, there's no concept of a small number of examples when it comes to a kid or a person learning. Because if we take the theoretical view that the biological system is learning by analogy, there will always, there's a lot of data. Okay, the 2 years old, maybe it's the first time that they see a certain object, but it has a certain distances to a very large representational space. And because we work a lot by analogy, even if the kids have never seen how to use a certain folding table, the kids did play with books and putting things on the top. And by this analogy, the transfer on analogy help people to learn, or kids to learn. And it might be that what we need for machine learning model is to be able to have algorithms that work like analogy. That might be one step forward in order to start having system that can generalize, like you were explaining, Vint.
This is very helpful, thank you, because what you suggested, at least to me anyway, is that among the things that we use with great power is metaphor and analogy. So we say this thing is like that thing, or some of the characteristics of this thing look like that thing, and I know something about that thing, so I will make a prediction that this thing will behave like that thing, and then test that philosophy or that theory, which, by the way, is fundamental to science. And it almost suggests to you that young people are, at core, they're scientists who are making predictions, formulating theories, and testing them. And then, unfortunately, too many of them lose interest in that wonderful discipline. But this raises a question for me about representation. And I'm still struggling a little because what Tom said about a verbal or textual description of something is one way of modeling an object, literally a textual description about the object and what it can do and what it's used for. Is that the right representation, though? Do you think that that when you look at a scene, when a program is looking at a scene, that the best way for it to represent what is in the scene is a text description of it? Or is there some other representation, or maybe there's more than one representation that's needed in order to understand how to manipulate what you're seeing in the scene? I'm wondering about representation here, because it's one thing to represent information by this gigantic statistical model with 1 billion parameters, which is probabilistic in nature, but doesn't necessarily lend itself well to reasoning and problem solving. So what kind of representations do we have now, or should we have, or will we have, that allow us to think our way through how things work?
May I just clarify a tiny bit? I don't think the representation should be language-based. I think the representation can be reconstruction-based, affordance-based, cross-modality, consistency-based, all of these things that are very rich, dense signals that can be grounded and supervised at scale. I think if a person has a definition, they want to create an interface to the model, language is a very rich way to do that. And humans are relatively lawyerly with our language, trying to carefully define, for example, your definition of a table. I have a 3-year-old. If she used that definition of a table, I would be quite upset. So I think, again, language is an interface to something with a far richer implicit representation that can do reconstruction, that is consistent with simulation, that is cross-modality consistent. That can be learned embodied or learned via observation is actually what I was trying to convey. Sorry.
In the previous panel, we were talking about direct brain interfaces. And of course, that got into great complexity when we reached the cognitive space as opposed to the sensory neural and sensory motor space. And I'm now imagining that as we sense the real world, in this case through vision, that maybe there are more than one model might have to be generated in order for us to both understand and interact with the scene that we're observing. Marshall, your microphone is off. No, I mean, the microphone is on, and so looks like you might want to say something.
Yes, yeah, I just wanted to elaborate on what Tom just said earlier, and what you're asking about the representation. I think it's unrealistic to imagine that there is a single representation that will be ideal for all possible tasks, all possible downstream tasks. And by that, what I mean by that is that there can be multiple representations that are more suitable for individual tasks, but that is different than the fundamental point of being able to acquire some knowledge to build those representations. That's where the language, I think that's what Tom was saying about the language, that's where that comes in, to facilitate that process. But then after that, to have an efficient representation for task A, B, and C, we can imagine different types of representation. So for example, there are certain tasks where it's useful to have some notion of 3D information, so some notion of geometry. There are other tasks where it's completely irrelevant, right? So you can imagine more specialized representation downstream.
This is really interesting because I often find myself having conversations and discovering a great clash because something I have said about a system or a problem or whatever that we're trying to solve or design makes no sense to the other person. And then there's this big argument, and eventually you realize that you have different mental models of the problem. And so the other person's description of the problem or the solution makes no sense at all. And so you back away and you say, well, let's make sure we have the same model of the problem before we have an argument about how to solve it. And I don't know about you, but I find myself drawing pictures as a way of trying to understand how things relate to each other. And I'm also finding that certain abstractions are very helpful, getting rid of details that confuse the fundamental ways in which things work. Is abstraction an important part of computer vision? Dacheng.
I think this is very relevant to explainable deep learning. So we know that the current deep learning models are not explainable. So we don't know. So what do we really do with those data through our model? But actually, we can treat our foundation models as a super data storage or super distributed data storage database. So it seems that we really decompose the training data into small parts in a particular way, but not just segment those data into small segments and then store them in the network, but actually by using some nonlinear strategies to decompose our images or our videos into parts so that our foundation model can efficiently record those training data. And then our model also has its a way to recompose all the decomposed parts so that we can recover the training data. So given this, so we already found that such like GPT-2 actually record the training data. So that means people can find ways to attack those models and can recover the training data. But if we really understand, so what is the distributed storage mechanism used in our foundation models, so that means we know how can we deal with our models, and then in the future, the representation or the learning or the adaptation will be much easier. Thank you.
Thank you. Just as an acknowledgement, apparently my camera is on my laptop, but it is apparently not feeding video to the Zoom session. So I'm just a black hole now, out of which sound is coming. And if I disconnect and reconnect to correct the video problem, I will lose the entire context of all the chat and the Q&A. And so to avoid losing context, I'll continue to be the voice of God coming out of the dark. And I apologize for that. We don't know why it's behaving this way. Did anyone else want to respond to what Dacheng just said?
Yeah, I think abstraction has to be an essential component of computer vision. Let me give you an example. Let's say you have a collection of events that your system is looking at in the world. You have the notion of exercising. Well, that can be swimming, running, weightlifting, and so on. So, but also exercising and biking are both examples of moving and so on. So abstraction is this notion that a collection of different set task, different event belongs to the same set, exercising or moving. And I think that what some work in the past have shown is that if you have a new event coming in, it's actually better to have it categorized at an abstraction level, at least moving or exercising, than having an error. So in a way, just very concretely, if you have a system that can reason at different level of abstraction, in this example for event recognition, it's a way to make less error, or if there is error, the error make more sense, and avoid some catastrophic error, or even being able to recognize new events.
I'm nodding my head, even though you can't see that.
We hear you.
Yeah. So this is suggesting that do we actually know how to do abstraction in the visual scenes right now? Do we have a regular way of analyzing a scene and building a representation of it which abstracts away from some of the detail which may not be important? For example, the fact that there is a table in the scene may be more important than the color of the table or even the shape of the table. The fact that it's a table imbues that scene with a certain functionality. And yet, if we were talking about the design of the room, we might care a great deal about the shape of the table and its size and its color or its other decorations. So finding the right level of abstraction for understanding or solving or doing reasoning about a scene seems very important. And I don't know anything about the state of the art at this point of scene representation, what's going on in this scene. It gets more complicated if I'm asking the system to observe a video segment and explain what happened in that, or what do I make of this video segment? So where do we go with that kind of understanding?
Well, maybe my colleagues will disagree with what I'm about to say, but this is again
where
that's the point of the panel, right? That's again where I believe that you cannot address those questions in a task-independent way. In other words, there is a core representation that you want as compact and efficient and rich as possible, but then how you go further, right? Depends entirely on the task. One example that I give quite often is the following, right? The basic image segmentation problem is basically labeling pixels, right? And the implicit loss function here is minimizing the number of pixels that are mislabeled or trying to label all the pixels correctly. Simplifying a little bit, but roughly speaking. If you think about it, there is no task that requires, for example, self-driving, that requires every pixel labeled correctly, right? So, yeah. In other words, we building your representation or solving your problem that doesn't match the problem with the task. And I don't know that we know how to do any of this, right? What we're making big progress on is the things we talked about earlier. I mean, those core representation, in particular now using language to help us, and they are very powerful and rich representation. I think and again, people might disagree, what we don't know how to do is to take that core representation and now extract just what we need for the specific task that we want to do right now. Right?
Thank you. Thank you. The context thing is such a valuable idea here, because you're quite right that if we are trying to do something, then the system that is helping us do it needs to have some notion of what the intent is. And then it has to have some notion of what does it need to know, and at what level of specificity does it need to know in order to accomplish the task. I want to go off on a tiny tangent for just a second. I had an opportunity to watch a video of an Amazon warehouse that had robots moving around and apparently not running into each other, which I was impressed by. Filling up boxes to then be shipped somewhere. And apparently the system is pretty good, not only at getting to the right place to select and to pick the product, but also to recognize whether it got the product or not. Is that something that has required a really significant advance in computer vision, or is that sort of just state of the art? Okay, I should go ask Bezos that question. Fair enough. But it does raise an interesting question about current day capability for object recognition and manipulation. I mean, I seem to remember an experiment that we did at Google once where we had a robot that was trying to sort objects and toss them into the appropriate bins. And it got pretty good at recognizing what it had just picked up and then literally tossing it several feet away to land in a particular box. And this was, I don't know the details of how it did that, but it was largely based on the kind of large models, high dimensional models, where it learned to associate this image with the thing it was supposed to pick up and which box it was supposed to go to. And it learned experimentally how hard to fling whatever it was into the box. And the objects were quite varied kinds of shape, a ball or a bag or, a telephone headset or something else. So I don't know how hard it is to build up a model that allows the system to make decisions like that. But it must be, we're back to Marshall's observation that task context has a huge role to play in the value of any particular model that has been built.
If I may add some thought to this, so to me, I like to think of those questions in terms of the size of the world, the robot, or the task it has to do. So, like if we play a game, if we play chess, or if we play another game, this is our world, a closed world. So I cannot say what's happening in the warehouse, but I will think that if there is, let's say, a robot has a limited motion, or even if it's a given space, it's to me a world that is closed in terms of the size of the package that can come and the type of material those packages are. So it's a very large space, but it's still a world that can be simulated potentially with a lot of synthetic data. So maybe 10% of real data and the rest are synthetic data. And those will be cases where you could see feats of performances like that, potentially because the world is closed in a way. It's limited. It's not like the car going off the road, which is really one aspect of it. Huh?
That's a really helpful observation, because if the world has a set of rules for the way it works, just like a Go game or a chess game has a set of rules for the way it works, you constrain a lot of the dimensionality of the problem. And it makes it more feasible for the computer vision to recognize things and to manipulate things.
Which actually make me think of a funny is that if suddenly those robots with a sort of hands, we give them a sort of marshmallow or something that if you touch it becomes water, not sure the system will be able to know how to react to that. It might be really outside the representation, but anyway. It's just a joke.
Exactly. That's a very good point.
Yeah, actually, sorry, can I add one thing to what Aude just said?
Of course.
This raises one thing, and again, my colleagues might disagree with this, but it raises one thing that I believe we really, really don't know how to do, or do in a formal way in computer vision right now, which is knowing what we don't know, or more precisely, knowing that we don't know. In Aude's example, the vision system is now operating in a world that it has not been trained on. Okay, that was an extreme example, but real example happen all the time with self-driving, for example, right? So you cannot expect a vision system to operate all the time under all conditions in the universe. But what you really want is for the vision system to be aware that it is now in a situation where it cannot operate properly. That, I believe, we don't know how to do, okay? And that's different from improving the performance of the vision system, yes, right? Whether it's 95%, 99%, at some level, I don't care at some point. What I care about is that if now you're in a different condition, you're not going to give me an answer. That's very hard, even for your basic deep learning network, right? A deep network. It's always going to give you an answer. Maybe it's going to give you some confidence, but that's questionable at best.
Yes. You just used the word that I wrote down before you said it, which was confidence. And having a system even be aware of the fact that it is not confident of its identification, for example, this thing is an X, but I'm only 10% sure that it's an X, it might be a Y. And I do wonder whether we need to build into these recognition systems some notion of confidence, so that this, as you suggest, that the system knows when it is operating in a space where it is uncertain about what to do. Certainly the self-driving cars are trained, at least ours are, I think, to recognize that there is a condition it doesn't know what to do about. And so it goes into some sort of safe mode, just like spacecraft do that, you know, when they detect the condition that's potentially hazardous, they go into what's called the safe mode. So the idea, I don't know what to do, is important.
Yeah, so individual engineered system, like the Waymo self-driving car, they all do that because they have to. The problem is, as far as I know at least, there is no systematic approach, right, or theory or things like this that would help us do that.
Yeah, it's sort of like everybody wants a theory of everything, and if we don't have that, we have to have a theory of what we don't know. But that's sort of like the unknown unknowns, that the popular expression. Tom, it looked like you were about to say something or do something, but am I misinterpreting your image?
No, I was thinking about responding. That language is, in a way, the most natural and efficient abstraction. And that's how I view language here. And it may not be appropriate for the robots that are tossing something into a trash can to try to encode the trajectory in language, because that's not how a human does it. In fact, we don't even have great words for saying 2 degrees to left and up, and that isn't expressed that way. That's an affordance, that's a reconstruction and prediction and causality thing. And that feels like a fundamental kind of thing that we can build. But like the history of computer vision is going from a couple of these abstractions like ImageNet or JFT or something like this, where you have a taxonomy of classes that are as calibrated as possible, to getting into more of an open world where the way a person describes a scene is influenced by what is most informative in the scene, what is out of the ordinary. And so, if you asked me to describe the background behind Marshall, I probably wouldn't spend a bunch of time talking about the drop ceiling and the construction and the fact that all these squares come together properly, because it's just a drop ceiling, done. That's, there's these kind of shortcuts that we've taken, these abstractions in language. And I think that's why we've seen this huge uptick in the amount of supervision available to these models, is because now they have the capability of working in this kind of ultimate abstract space. But I still feel that that abstract space is not the end supervision of the robots or the embodied agents of the future. That feels like it's something more the interface, because in the end, they do have to be able to say, that part of the drop ceiling needs a repair, or this part here needs to be fixed, in ways that a human wouldn't express in words necessarily. Sorry, it was the mix between the Amazon robots not colliding and the language abstraction that made me kind of want to reinforce vision first.
This, again, I'm sorry for being the black hole here, but this makes me think, Tom, of a situation where we have recognized it's an X for some value of X. And the fact that we recognize something as an X should invoke a whole bunch of other things we know about X's. And the representation of that knowledge about X could be it doesn't have to be confined to any one particular modality. So it could be a text description of what an X is, but it might be other models of how X's behave or how they can be manipulated or some other thing along those lines. And so this makes me imagine that our successful use of machine recognition and scene analysis, object recognition, and the like, it will be usefully combined with a variety of different ways of knowing, representing, and knowing about those objects, which makes me think of knowledge graphs. And I don't know very much about how knowledge graphs are actually constructed. I don't know if it's purely a textual thing or whether there's some other representations that are in there. But it does seem to me that we need to be able to invoke something like that. What do I know about the thing that I have just recognized? And that must be a part of the more general utility of image recognition or object recognition. So are there breakthrough areas that are needed, or do you think that we have an ample supply of representations that we can associate with having recognized something?
Hi, Vint. Yeah, actually, a few days ago, I asked the ChatGPT some questions about the form of the future interface. So it predicts that the voice-based interfaces will become more popular with the advancement of voice recognition technology. Augmented reality and virtual reality will play important roles in the future of interfaces, and touch screens will continue to be important with the haptic feedback technology improving the user experience. Wearables will also be a significant part of the next generation of interfaces, continually collecting data and providing feedbacks. So to me, I think it's very clear that those answers provided by ChatGPT are very interesting and also very collective. So they are comprehensive and well organized and drawing on its vast training data. So however, it's also true that ChatGPT lacks a certain level of creativity and imagination. So I think today we have very extensive discussions about the possible tech trajectories of machine vision or computer vision for the future interface. So these advancements in vision will lead to, I think, be more natural, immersive, and personalized interfaces that better understand and respond to users' behavior with context. Eventually, I think we may interact a virtual super AI agent instead of physical entities, where we can see that IoT sensors will be everywhere, so that information, especially the visual information, can be easily collected. So that means, so we're going to be intangible, and I think intangible is much better than tangible.
Well, we are just about out of time, so I think trying to ask more questions may not work very well. But let me just try to summarize what I think I've heard, which is that we are already at a fairly sophisticated state of the art of being able to recognize scenes, recognize objects in the scenes, and apparently even reason to some extent about what's happening in the scene. That suggests to me that we can improve on our ability to understand what I'll call local conditions. You know, what is the what situation am I in right now? You know, imagining the airport security monitor trying to interpret what it's seeing and alerting in the event that it sees something that is out of the ordinary. Again, there's an important component of prediction there. We predict that this is what I am seeing is ordinary. We predict that what I am seeing is safe. And then we see something that is not normal and not predicted, therefore we alert because there might be a problem. Well, maybe we can look forward 20 years from now to systems that are better able to model their environment and what they are seeing around them in order to either solve problems for us or with us. And that would be a big benefit.